Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1915 publication Invariant Variations problem by Emmy Noether represents a monumental articulation of a deep physical and mathematical principle, a work whose elegance and power continue to resonate through the foundations of modern science, originating from a specific puzzle within the nascent theory of general relativity posed by David Hilbert and Felix Klein. Noether's paper transcends its initial context to establish a universal connection between the symmetries of a physical system and the conservation laws that govern it. This essay undertakes a rigorous, section-by-section evaluation of the internal claims and logical architecture of Noether's paper. It will dissect the mechanisms she introduced, assess the coherence of her arguments, and explore the profound consequences of her two celebrated theorems as they are presented within the text itself. The analysis will proceed through the paper's logical development, examining the foundational claims, the formulation of each theorem, and their application, thereby illuminating the work's self-contained intellectual prowess and its enduring contribution to theoretical physics and mathematics. Section 1. The formulation of the invariant variational problem. Noether begins her paper by meticulously establishing the mathematical landscape. Her central object of study is an integral, specifically an integral over a multidimensional space, whose value depends on a set of field functions and their derivatives. This formulation, expressed as the integral of a function, which we identify as the Lagrangian density, over a region of spacetime, is the formal representation of the principle of action. Her initial claims center on the concept of invariance. She posits a group of continuous transformations which can alter the coordinates of the spacetime and the values of the fields themselves. The core premise is that the action integral remains unchanged under these transformations. This invariance is the mathematical expression of a physical symmetry. She defines this continuous group using a finite number of parameters, where the transformations become the identity. When all parameters are set to zero, her framework is one of astonishing generality. The specific form of the Lagrangian function is left arbitrary, as are the number of dimensions of the underlying space and the number of field functions. This abstract approach allows her conclusions to possess a universal applicability, covering a vast range of physical theories from classical mechanics to electromagnetism and beyond. The argument in this opening section is primarily definitional. Its strength lies in its precise and comprehensive construction of the mathematical apparatus required for the subsequent proofs. She carefully lays out the infinitesimal form of the transformations, considering changes that are linear in the small parameters of the symmetry group. This focus on infinitesimal variations is the crucial methodological choice that unlocks the entire deductive chain of the paper, allowing her to employ the tools of calculus to explore the consequences of a global symmetry at a local level. Section 2. The derivation of the first theorem. Following the formal setup, Noether presents her first, and most famous, theorem. The central claim of this section is that for every continuous symmetry of the action integral, there exists a corresponding conservation law. This is a direct, constructive proof that links two previously disparate concepts into an inseparable pair. Her method of evaluation is a masterclass in logical deduction. She considers the variation of the action integral in two distinct ways. First, she computes the variation that arises from the infinitesimal symmetry transformation she defined in the preceding section. By the core assumption of invariance, this variation must be equal to zero. Second, she computes the variation in the standard way used to derive the equations of motion, leading to terms involving the Euler-Lagrange expressions. By equating these two calculations of the same variation, she forges a powerful identity. The genius of her argument resides in the next step. She assumes that the field functions satisfy the equations of motion, meaning that the Euler-Lagrange expressions are themselves equal to zero. This is a critical move. The theorem applies to physical trajectories, to systems that obey the laws of physics derived from the principle of least action. Under this condition, the identity she derived simplifies dramatically. It reduces to the statement that the divergence of a particular combination of quantities is precisely zero. This combination, a vector-like object constructed from the fields, their derivatives, and the generators of the symmetry transformation, is what we now call the Noether current. The condition that its divergence equals zero is the differential form of our conservation law. Integrating this expression over a volume of space and applying the divergence theorem yields a conserved charge, a quantity whose total amount remains constant in time. Her claim is thus proven in its full generality. The evidence is entirely mathematical, arising from the logical consequences of the initial premises of continuous symmetry and the validity of the equations of motion. The mechanism is a brilliant manipulation of the variational calculus, demonstrating that conservation laws were a structural consequence of the symmetries inherent in a theory's formulation, and deep truth about the architecture of physical. Section 3. The introduction of infinite parameter groups. The paper then transitions to a more complex and subtle domain, one directly motivated by the challenges of general relativity. Noether expands her analysis to encompass symmetries described by infinite parameter groups, sometimes referred to as gauge symmetries. In this case, the transformations depend on arbitrary functions of the spacetime coordinates, rather than a finite set of constant parameters. For example, the freedom to redefine the electromagnetic potentials or the coordinate system in general relativity constitutes such a symmetry. The central claim of this section is profoundly different from the first theorem. She argues that the existence of an infinite parameter symmetry group implies a set of identities among the Euler-Lagrange expressions themselves. This means the equations of motion derived from the action principle are interdependent, they are linearly dependent. This revelation, which constitutes her second theorem, shifts the focus from conserved quantities to the internal consistency and structure of the physical laws. The methodology again relies on a careful analysis of the variation of the action integral. Since the symmetry transformations now depend on arbitrary functions, she can analyze the consequences for the variation term by term in a power series of these functions and their derivatives. The requirement that the action remains invariant for any choice of these arbitrary functions imposes severe constraints. It forces certain combinations of the Euler-Lagrange expressions and their derivatives to vanish identically, independent of whether the equations of motion are satisfied. These are the Noether identities. The assessment of this claim reveals its deep significance. It demonstrates that theories with gauge symmetries possess a built-in redundancy. The equations of motion are a constrained system, and some of them are consequences of the others. This is a structural feature of the theory, a direct result of its fundamental symmetries. The ether of a captivating historical anecdote hangs over this part of the work. One imagines the intellectual satisfaction in demonstrating that the perplexing interdependencies within gravitational field equations were a predictable feature, a beautiful consequence of a general principle. Section 4. The application to Einstein's general theory of relativity. In the final substantive part of her paper, Noether applies the formidable machinery of her second theorem to the very problem that initiated her investigation, the conservation of energy in Einstein's theory of general relativity. At the time, there was considerable confusion, particularly in the Göttingen circle including Hilbert, about the apparent failure of a straightforward energy conservation law in the new theory of gravity. The core argument of this section is that this apparent failure is a direct and necessary consequence of the theory's fundamental symmetry, which is general coordinate invariance. This symmetry, the principle that the laws of physics must be formulated in a way that is independent of the choice of coordinate system, is an infinite parameter gauge symmetry of the type analyzed in her second theorem. Noether applies her theorem to the Einstein-Hilbert action. For gravity, she demonstrates that the general covariance of this action leads directly to a set of identities, which are precisely the contracted Bianchi identities. These identities show that the divergence of the Einstein tensor is identically zero when the Einstein field equations are imposed, which state that the Einstein tensor is proportional to the stress-energy tensor of matter and energy. This identity implies a crucial result. The covariant divergence of the stress-energy tensor must be zero. This is the mathematical statement of local energy momentum conservation in curved spacetime. However, it is a more subtle law than the simple conservation laws of her first theorem. Due to the nature of covariant derivatives, one cannot simply integrate this local law over a finite volume to obtain a globally conserved quantity in the same way one can for electric charge. She shows that the conserved quantity associated with general covariance is what became known as a pseudotensor. Its value depends on the coordinate system, and it can be made to vanish at any given point by a suitable choice of coordinates. Her evaluation here is devastatingly clear. The lack of a simple, unique, localizable energy density for the gravitational field is a feature, a direct consequence of the equivalence principle and the gauge symmetry of the theory. She resolves the paradox by showing that the very structure of the theory forbids the kind of conservation law that physicists have been seeking. The energy conservation issue in general relativity is thereby recontextualized from a perplexing problem to a profound insight into the nature of gravity itself, a resolution whose tidiness and intellectual depth are a hallmark of her entire approach. In conclusion, Emmy Noether's invariant variations problem stands as a work of supreme intellectual synthesis and analytical power. The internal claims of the paper are advanced with impeccable logical rigor, moving from a general axiomatic framework to two powerful theorems of immense physical consequence. The evaluation of her method reveals a profound reliance on abstract mathematical structures to uncover deep truths about the physical world. Her first theorem provides a universal algorithm for discovering conservation laws, transforming the search from a series of ad hoc discoveries into a systematic procedure rooted in the identification of symmetries. The second theorem offers an equally deep insight into the structural constraints that symmetries impose upon the laws of physics, revealing the nature of redundancy and interdependence in gauge theories. Our application of the second theorem to general relativity resolved a critical foundational issue, demonstrating that the conceptual framework she built was capable of taming the most challenging theoretical problems of her era. The paper's lasting significance derives from this very quality. Its claims are so general, its methodology so powerful, and its conclusions so fundamental that it provided a new language and a new set of tools for theoretical physics. It laid a mathematical foundation upon which much of 20th century physics, from quantum field theory to the Standard Model, would be built, forever enshrining the principle that symmetry is a primary, guiding concept in our understanding of the universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.